Hi, my name is Pravit, and this is the video lab report for Experiment 3. The purpose of this lab was to explore the behavior of DC circuits using the circuit construction kit simulation on Phys. We used the principles of charge conservation and energy conservation to predict and then measure currents and voltages in a series resistor circuit. We also investigated how capacitor charges and discharges in an RC circuit, and used that data to compute the RC time constant. The key results: in the series circuit, we measured current 20.4 milliamps and confirmed that the potential differences around the loop sum to exactly zero. In the RC circuit, our measured time constant was 6.01 seconds, essentially identical to the theoretical value of 6 seconds. Three core physics principles. First, charge conservation, sometimes called the current rule. In steady state, charge doesn't pile up at any node in the circuit. In a series circuit, this means the current is the same everywhere. Both ammeters read the same value. Second is energy conservation, expressed through Kirchhoff's loop rule. The sum of all potential differences around any closed loop must equal zero. The potential rise across the battery equals the sum of the potential drops across the resistors. And third is Ohm's law and exponential RC decay. For resistors, delta V equals IR. For a discharging capacitor, the voltage decreases exponentially with time as delta V equals delta V naught times e to the negative t over RC. Taking the natural log of both sides turns this into a linear relationship, so a log linear plot lets us extract the time constant RC directly from the slope. The system of the circuit loop itself, the surroundings of the battery, the energy source. Connecting wires are treated as ideal, meaning zero resistance. The series circuit consists of two 1.5 volt batteries in series for a total EMF of 3 volts, connected to a 47 and 100 ohm resistor with 2 ammeters. Before running the simulation, I predicted the current. Total resistance is 47 plus 100 ohm equals 147 ohms. By Ohm's law, I equals V over R equals 3.0 over 147, which is approximately 0.0204 amperes, about 20 milliamps. Since this is series circuit, charge conservation tells us both the ammeters must read the same value. The CCK confirmed this prediction. For question 3, when I reversed one ammeter, it was reading at a negative 0.204 amps. Negative because conventional current now enters its negative terminal. For question 4, replacing one ammeter with the voltmeter reads 3 volts and the ammeter drops to 0 because the circuit is broken at the voltmeter gap, so no current flows, but the voltmeter measures the full battery EMF. Next, I measured the potential difference across each segment of the circuit. Going around the loop across the battery, the potential rises by plus 3 volts. Across the wire from B to C is 0. Ideal wire, no resistance. Across the 47 ohm resistor from C to D, it drops by negative 0.96 volts. Wire from D to E is 0. Across the 100 ohm resistor from E to F, it drops by negative 2.04 volts, and the wire and ammeter from F back to A is 0. For question 7, the theoretical sum around a closed loop must be 0, and in D, positive 3 minus 0.96 minus 2.04 equals exactly 0. Energy is conserved. The battery supplies exactly the energy dissipated by the two resistors. For question 12, calculating resistance from these measurements, delta V over I gives 0.96 divided by 0.0204 equals 47.1 ohms for the first resistor, and 2.04 over 0.0204 equals exactly 100 ohms for the second. The wires and ammeter both give 0, consistent with their ideal behavior. Question 8 asks us to plot the electric potential versus position around the circuit. Starting at point A at 0 volts, the potential jumps to 3 volts at B across the battery. It stays flat at 3 volts from B to C. Wire segment, no drop. Then it steps down by 0.96 volts across the 47 ohm resistor to 2.04 volts at D. Flat again from D to E. Steps down 2.04 volts across the 100 ohm resistor to 0 at F. Then flat at 0 all the way back to A. The steeper the slope on this graph, the stronger the electric field in that region, and the field is largest inside the resistors. Questions 9 through 11 explored what happens when we change the meters. Question 9. Adding a voltmeter in parallel doesn't change the ammeter reading because an ideal voltmeter has infinite internal resistance. Essentially, zero current flows through it, so the rest of the circuit is unbothered. Question 10. Connecting the voltmeter across a 100 ohm resistor, the ammeter still reads approximately 0.02 amps for the same reason. Question 11. Replacing the voltmeter with an ammeter in parallel with the 100 ohm resistor is very different. An ideal ammeter has zero resistance. It short circuits the 100 ohm resistor entirely. All current bypasses it and flows through the zero resistance ammeter instead. Now only the 47 ohm resistor limits the current. I equals 3 divided by 47, which is approximately 0.064 amps, a jump from 0.02 to 0.064. Section 3 explored RC circuit behavior using a capacitor, battery, and light bulb. When I connected the battery, capacitor, and 10 ohm bulb in series, the bulb started bright and gradually dimmed. The current decreased as the capacitor charged up because the growing charge on the capacitor's plates increasingly opposed further current flow. With the 10 ohm bulb, charging took about 3.89 seconds. With the 20 ohm bulb, it took 10.13 seconds. More resistance means a longer time constant. When I disconnected the battery and let the capacitor discharge through the bulb alone, the bulb lit up again and faded. The stored charge drove the current decreasing exponentially as the capacitor drained. Section 3.1 quantified the RC time constant. I set up a 9 volt battery, 200 millifarad capacitor, and 30 ohm resistor in CCK. Recorded the capacitor voltage every second for 20 seconds and plotted in natural log of delta V over delta V naught against time. This should give a straight line with slope equal to negative 1 over RC. From a linear fit to my 20 data points, the slope was negative 0.1664 per second, which means that RC measured equals 1 over 0.1664, which is 6.01 seconds. The theoretical value is 30 ohms times 0.200 farads, which equals exactly 6 seconds. That's a difference of less than 0.2%. Excellent agreement, confirming the exponential decay model for RC circuits. 2 what if questions. First, what if we use a real ammeter instead of an ideal one? A real ammeter has small but non-zero internal resistance, typically a fraction of an ohm up to a few ohms. In a series circuit, this adds to the total resistance and reduces the current. For a 147 ohm circuit, even a 1 ohm ammeter resistance would reduce I by less than 1%, small but measurable effect. In low resistance circuits, the impact would be much larger and could seriously distort results. Second, what if we charge the real capacitor with no resistor at all? With R equals 0, the RC time constant is 0, and the ideal model predicts instantaneous charging. The capacitor fills up in 0 time. But this is physically impossible. In reality, every battery has internal resistance and every wire has resistance. With negligible total resistance, the instantaneous current would be enormous, potentially hundreds of amps, enough to melt wires, blow fuses, or destroy components. The ideal RC model breaks down entirely in the R approaching 0 limit. Few sources there with no CCK use ideal components, perfect wires, ideal ammeters, ideal voltmeters. In real life, none of these are truly ideal. Ammeters have small resistance, voltmeters have finite resistance, with wires have measurable resistance at high current. Timing the RC discharge introduces quantization error since we read voltage at discrete time steps rather than continuously. Our 0.15 RC error is likely dominated by this. Real batteries also have internal resistance that reduce the terminal voltage under load, and light bulbs aren't truly ohmic. Their resistance increases with temperature, making the RC timing measurements with bulbs approximate rather than exact. To summarize, both ammeters and series circuit read 20.4 milliamps, confirming conservation. All measured potential differences summed to 0, verifying Kirchhoff's loop rule. Ohm's law checks gave resistances matching nominal values within measurement precision, and the RC time constant from our discharge data was 6.01 seconds, a 0.15% match to the theoretical 6 seconds flat. The CSK simulation confirmed our predictions, cleaning with ideal components, eliminating the complications that real lab equipment would introduce.